Ever just watch popcorn pop? Like, it's
Sure.
fascinating, right? You get that heat going, and those kernels start going crazy.
It's totally a mini explosion in every kernel.
It really is. And that's like energy just transforming right in front of you. That's actually a great visual for what we're going deep on today.
Yeah, great analogy. Today we're going to be tackling the first law of thermodynamics. And, you sent over this chapter, pretty dense stuff. We're going to try to break down the basics, see how energy moves around in systems and why this law is so important. Like, it's a pretty big deal for understanding a lot of stuff from, that popcorn popping to like huge power plants and how they work.
Okay, so this chapter starts by talking about these things called thermodynamic systems. What exactly is a thermodynamic system?
So, a thermodynamic system, think of it like this. It's any part of the universe that we choose to focus on. It could be something small and contained like a pot of popcorn, or it could be something massive like the Earth's atmosphere, or it could be something in between like a biological cell. The key is that it's a defined region, and there are boundaries, real or imaginary, and those boundaries separate the system from its surroundings. And the surroundings is everything else that can potentially exchange energy with it.
So if we're talking about popcorn, our system is those kernels,
Yeah.
right? And the surroundings would be like the pot, the stove, the air around it, all that stuff.
Exactly. And the chapter really emphasizes this. It says that the first step is to define your system very clearly. Because if the boundaries are unclear, it becomes really hard to keep track of where the energy is coming from and where it's going. Like if we included the pot as part of our system, then the heat going from the stove to the pot, that would be considered internal to the system. But if the pot's part of the surroundings, then that same heat flow would be considered an input to the system.
So we got to draw that line in the sand first, decide what's in and what's out. Okay, so we've got our system all defined. What happens next? The chapter mentions this thing called a thermodynamic process.
Right. So a thermodynamic process is basically any change in the state of the system. And by state, we mean the set of properties that describe the system at a certain point in time. So things like temperature, pressure, volume, internal energy, all that stuff. So when those kernels of popcorn heat up, the temperature changes, right? The pressure inside might build up. Maybe there's a little expansion before the popping, and then boom, huge increase in volume.
A very dramatic change.
Definitely. So all those changes together, that's a thermodynamic process.
So it's the journey that our system goes through from one set of conditions to another.
Right.
Okay, so now to get into how energy is involved in all this change, the chapter introduces the concepts of heat and work. How are these two things defined when we're talking about thermodynamics?
So, in thermodynamics, when our system exchanges energy with its surroundings, it's got two main ways to do it. It can exchange energy as heat, which is symbolized by Q, or it can exchange energy as work, which we symbolize with W. So, heat is energy transferred because of a temperature difference. Things tend to even out, hot to cold and all that. Work, on the other hand, is energy transferred by a force moving something over a distance.
So like if I push a box across the floor, I'm doing work.
Exactly, you're using force and moving at a distance.
And the chapter points out that it's not just whether energy is exchanged, but the direction is really important too, right?
Yeah.
Like the plus or minus signs for Q and W.
Yeah, those signs are crucial. They tell us if the energy is going into or out of our system. So by convention, when heat's added to the system, it's considered positive Q, and that's a gain for the system. If heat flows out, it's negative Q, which means the system's losing energy. Same deal with work. If the system does work on the surroundings, that's positive W energy is leaving. And if work's done on the system, it's negative W, that means energy's flowing into the system. And the chapter has a nice diagram for this, figure 19.3.
Okay, so plus signs mean the system is gaining energy, and minus signs mean it's losing it.
Right.
Makes sense.
Yeah.
So early on, the chapter kind of narrows its focus to a specific kind of work that's done when a system's volume changes. Why is that type of work so important in thermodynamics?
Well, it's actually super common for volume to change in thermodynamic processes. Like think about steam expanding in a turbine, or a car engine where those combustion gases push a piston, or even a hot air balloon. The air inside expands and that makes it rise. In all these cases, the system's boundary is moving. If it's expanding, it's doing work on its surroundings. If it's being compressed, then the surroundings are doing work on it. And yeah, our popcorn, when it pops, it expands, right? It might even push the lid off. That's a small-scale example of this kind of work in action. To help visualize this, the chapter uses this model of a gas in a cylinder with a movable piston.
Yeah, I remember that from physics class. Classic setup. So how does this gas and piston picture help us understand the work that's happening at like a molecular level?
Well, picture those gas molecules bouncing around inside the cylinder. When the gas expands and pushes that piston out, those molecules are colliding with a moving surface, right? They're basically smacking the piston and transferring a bit of their energy to it. That's work done by the gas, positive work. And when the gas is compressed, now the piston is pushing those molecules around, giving them more kinetic energy. So in that case, work is being done on the gas, and that's negative work from the gas perspective. Figure 19.4 in the chapter shows this really well.
So it's all about these tiny collisions between the gas molecules and the moving boundary. And all those tiny pushes and pulls add up to the macroscopic work we can actually measure.
Yeah, exactly.
So how do we put a number to this work that's done during a volume change? Like, is there a formula for that?
Oh, absolutely. For a tiny, tiny change in volume, which we call dV, and assuming the system is at a pressure P, the little bit of work done, dW, is given by this really elegant equation. dW equals P times dV. It's equation 19.1 in the chapter. Now, if we want the total work done when the volume changes by a decent amount, from an initial volume V1 to a final volume V2, and especially if the pressure might be changing during the process, we got to add up all those tiny bits of work. And that's where integration comes in. The total work is the integral of PdV from V1 to V2, which is equation 19.2.
Okay, so integration.
Right, because if the pressure isn't constant, we can't just use a simple formula. We got to take into account the pressure at every tiny step along the way as the volume changes.
Now, this integral stuff, I seem to remember it having a visual interpretation, something to do with the area under a curve. Am I remembering that right?
Yes. If we plot pressure on the axis and volume on the x-axis, we get what's called a PV diagram. And the work done by the system during a volume change is represented by the area under the curve on that PV diagram, between the initial volume V1 and the final volume V2. It's just like in physics, where work done by a force is the area under a force versus displacement curve. The chapter has a great visual for this too, figure 19.6. So if volume increases, meaning the system expands, that area under the curve is positive, which makes sense because the system did positive work. And if the volume decreases, if the system is compressed, then that area is considered negative because work was done on the system.
Okay, so it all comes back to areas and PV diagrams. Got it. Now, what if the pressure happens to be constant during a volume change? Does that make the calculation simpler?
Absolutely, it simplifies things a lot. If pressure P is constant while the volume changes from V1 to V2, then we don't need to integrate. The work done is just P times the change in volume, so P times V2 minus V1. Equation 19.3. On a PV diagram, this would look like a simple rectangle. The height is P and the width is the change in volume.
Yeah. Nice, simple rectangle. The chapter then goes through this example of an isothermal expansion of an ideal gas. Why is this specific case so important for getting all this?
It's a great example because it brings together a few key ideas. So isothermal means the temperature stays the same during the whole process. And we know from the ideal gas law that pressure, volume, and temperature are all related. So if temperature is constant during an expansion, then the pressure has to decrease as the volume increases. Now, since pressure isn't constant here, we can't use that simple formula we just talked about. We got to go back to that integral. And that's what they do in example 19.1. They use the ideal gas law, PV equals nRT, to substitute for pressure in the integral. Since N, R, and T are constant, we get pressure equals nRT over V. And they integrate that whole thing with respect to V from V1 to V2. The result you get is nRT times the natural log of V2 over V1.
Oh, right, that natural log pops up because we're integrating 1 over V. Now, I think the example also shows that you can express this work in terms of pressure, too, not just volume.
Yeah, because in an isothermal process for an ideal gas, pressure times volume stays constant. So P1 times V1 equals P2 times V2. We can use that to relate the ratio of volumes, V2 over V1, to the ratio of pressures, but flipped, so P1 over P2. When we plug that into the work equation, we get another way to express the same thing. Work equals nRT times the natural log of P1 over P2. The example then points out that during an expansion, V2 is bigger than V1, so that ratio is greater than 1. And when you take the natural log of a number bigger than 1, you get a positive result, meaning positive work was done by the gas, which is what we'd expect for an expansion.
Makes sense. Right after that example, there's a quick test your understanding question about expanding a gas. It asks about what happens when you double the volume at constant pressure versus at constant temperature. What's the main point that question is trying to drive home?
That question's all about emphasizing that work depends on the path taken. Like how you get from point A to point B matters. In the constant pressure case, the pressure stays low the whole time as the gas expands. But in the isothermal case, pressure starts higher and gradually decreases as the gas expands. So the path's different. And since work is the area under the PV curve, and the curve's shape is different for those two cases, the work done will be different even though the volume change is the same. In fact, the isothermal expansion ends up doing more work.
So the how really matters, not just the how much.
Exactly. The path is crucial.
And this leads us right into the idea that the specific path taken during a thermodynamic process is really important. Like, it's not just about the starting and ending points.
Yeah, exactly. A system can go from its initial state to some final state in countless ways. There are infinite paths. The chapter shows this really well with figure 19.7. And what it highlights is that the work done by the system during this change, it doesn't just depend on those endpoints, it depends on the specific path taken to get there. Because different paths on a PV diagram will have different areas under the curves, which means different amounts of work done.
And this whole path dependence thing, that's not just true for work, is it? I think the chapter said that heat transfer also depends on the path.
Oh yeah, definitely. Figure 19.8 uses that isothermal expansion example again to show this. So imagine the gas expands slowly, and it's in contact with a heat reservoir. So it's absorbing heat and doing work. That's one path. But now imagine that same gas expands freely into a vacuum. No work is done because there's nothing to push against. And if the container's insulated, there's no heat exchange either. Now, the starting and ending points, same temperature, same volume, they're identical for those two scenarios. But the amount of heat exchange and the work done are completely different. That really shows you that both heat and work, they depend on the path, on the specifics of how the change happens.
So same destination, different journeys.
Exactly.
Okay, so this path dependence has a pretty big implication, right? It means we can't really say that an object contains a certain amount of heat.
You got it. Because the amount of heat transferred to get a system to a particular state depends on how it got there. Heat can't be a property of the state itself. It's more about the energy that was transferred during the process. It's not something the system possesses. It's something that happens to it.
So we don't say an object contains work, and we don't say it contains heat. They're both about energy in transit.
Exactly.
But then the chapter introduces this concept that is a property of the state, internal energy. What's the difference between that and heat and work?
This is a key distinction. Internal energy, we usually represent it with the letter U, and it's the total energy stored within a system. It comes from the kinetic and potential energies of all the atoms and molecules making up the system. It's all the energy tucked away inside.
Okay, so how do we measure this internal energy then? Like, do we just count up all the energy of every single atom and molecule?
Well, in theory, you could, but in practice, that's not really feasible. There are just too many particles, and their motions are complex. What we can measure is the change in internal energy, which we write as delta U. And this is where the first law of thermodynamics comes in. The first law gives us this equation, delta U equals Q minus W equation 19.4. What this means is that the change in a system's internal energy is equal to the net heat added to the system minus the net work done by the system.
So it's a way to figure out how much the internal energy changed by looking at the heat and work, which we can measure directly.
Exactly. And notice that the equation only tells us about the change in U, not the absolute value of U. It's kind of like with potential energy, we usually care about the difference, not the actual value at some specific point.
Makes sense. Now, here's the big question, and I think I know the answer. Is this change in internal energy, is it path dependent, like heat and work?
Nope. It's independent. That's the crucial part. Even though Q and W, they do depend on the path, their difference, Q minus W, doesn't. It doesn't matter how the system got from A to B, the change in U is the same. This is a huge deal in thermodynamics, and there's tons of experimental evidence to back it up. No matter what process a system goes through, if it starts at one state and ends up at another specific state, the change in its internal energy will be the same. This means internal energy is a state function. Its value only depends on the current state of the system, not the history of how it got there.
So it's like saying no matter how you get to the top of a mountain, you've still climbed the same elevation.
Exactly. That's a great analogy. And figure 19.10 shows this really well.
So the first law, it's not just about energy conservation. It also establishes that internal energy is a state function.
Right. The first law, in its different forms, it tells us that when we add heat to a system, that energy either increases the internal energy of the system or goes into work the system does, or some combination of both. It's energy conservation applied to thermodynamic systems.
Okay, so the chapter then looks at a couple of special cases, cyclic processes and isolated systems. What can the first law tell us about those?
Okay, so a cyclic process, that's when a system goes through a bunch of changes, but eventually ends up back at its initial state. It comes full circle. Now, since internal energy is a state function and the final state is the same as the initial state, the total change in internal energy over that whole cycle got to be zero. Delta U equals zero. And the first law tells us that delta U equals Q minus W. So for a cyclic process, the net heat added to the system has to be equal to the net work done by the system. They got to balance out.
So all the heat you put in, you get it back as work, essentially.
Right, over the whole cycle. Now, an isolated system, that's different. An isolated system, by definition, it doesn't exchange any heat or work with the surroundings. So Q equals zero and W equals zero. Again, looking at the first law, that means delta U, the change in internal energy, must also be zero. So an isolated system's internal energy stays constant.
Okay, so cyclic process, delta U is zero because it comes back to where it started. Isolated system, delta U is zero because it's totally cut off from the outside world.
That's it.
Got it. Now, I think the chapter lays out a strategy for tackling thermodynamics problems,
Yeah.
like a step-by-step thing. What are the main points to keep in mind?
Yeah, it's called Problem Solving Strategy 19.1. Super useful. First thing, you always got to define your system. What are you looking at, and what are its initial and final states? Then list out all the quantities. What do you know, and what do you need to find? Keep in mind, you're probably going to be using not just the first law equation, but also the definitions of work and maybe the equation of state for the material, like PV equals nRT for an ideal gas. And of course, make sure your units match up throughout your calculations. Don't mix apples and oranges.
Good advice in general.
Right. And the strategy also reminds us that delta U is path independent. So sometimes you can solve a problem even if you don't know every little detail of the path the system took. And lastly, if you have a process with multiple steps, make a table. Keep track of Q, W, and delta U for each step. That'll help you make sure everything adds up right in the end.
Good organizational tips. And then the chapter goes into a few example problems, like analyzing that cyclic process and comparing processes along different paths. Example 19.4, the one comparing paths to adiabatic. I think that one really showed how heat and work depend on the path, but internal energy doesn't.
Yeah, that example's great. It shows how you can end up at the same final state, starting from the same initial state, but take two totally different routes to get there. And along those different routes, the heat transferred and the work done will be different, but the change in internal energy, it's the same for both paths.
Another one I thought was interesting was the boiling water example. What does the first law tell us about that?
So that's example 19.5. It's looking at water turning into steam, but the pressure stays constant. It shows how the energy we add as heat gets used. Some of it increases the internal energy of the water molecules. That lets them overcome the forces holding them together as a liquid so they can become a gas. But some of that heat also goes into work, because water expands a lot when it turns into steam, and that pushes against the air around it. So the first law helps us understand where all that energy goes.
So budget for the energy.
Yeah, exactly.
Okay, towards the end of this section, there's a bit about the infinitesimal form of the first law. When do we need to think about these tiny, tiny changes in energy?
So those infinitesimal forms, we're talking about equations like du equals dq minus dw and du equals dq minus p to b. Those are really helpful when the pressure, volume, and temperature are changing continuously. In those cases, you often need calculus to analyze what's happening, integrating those tiny changes to find the total change over a certain period.
So it's for the more advanced stuff. God, now the chapter shifts gears and starts talking about different kinds of thermodynamic processes. There are four main types, right? Can you give me a quick rundown?
Yeah, we can break them down based on which thermodynamic property is held constant during the process. So first we got adiabatic processes, no heat exchange, Q equals zero. And that makes the first law simpler because now delta U equals negative W. So any change in internal energy has to come from work done by or on the system. Then there's isochoric processes. Those happen at constant volume, so delta V equals zero. No volume change means no work done, W equals zero. And the first law becomes even simpler. Delta U equals Q. All the heat added goes into changing the internal energy. Then we got isobaric processes. Those happen at constant pressure. Delta P equals zero. Here work can be done, and the first law is the full equation. Delta U equals Q minus P delta V. And finally, we have isothermal processes. Temperature stays the same. Delta T equals zero. For an ideal gas, that means delta U is also zero, so the first law becomes Q equals W. All the heat added is used for doing work, and figure 19.1c shows these different processes really well on a PV diagram.
It's helpful to see them all together like that. So adiabatic, isochoric, isobaric, isothermal. We've got them. Now there's this thing called free expansion, and I think the chapter says it's adiabatic even though no work is done. That seems a bit odd, doesn't it?
Yeah, it can be a little counterintuitive. Free expansion is when a gas expands into a vacuum. It's adiabatic because there's no heat exchange, but it also doesn't do any work because there's no external pressure to push against. So both Q and W are zero. And that means, from the first law, delta U must also be zero. Internal energy doesn't change during a free expansion.
So it's changing volume, but not doing work, which seems weird.
Yeah, it's unique to expanding into a vacuum. And this actually tells us something really important about the internal energy of an ideal gas.
Which is what the next section's all about. So what does this free expansion scenario reveal about the internal energy of an ideal gas?
Okay, so in a free expansion, we know delta U is zero. And experimentally, we also see that the temperature of the gas doesn't change. So what this tells us is that, for an ideal gas at least, internal energy only depends on temperature, not pressure or volume. It's a key part of the ideal gas model. And the chapter contrasts this with real gases, which aren't ideal. For those, the temperature does change during free expansion, which means their internal energy depends on both temperature and pressure.
So ideal gases, nice and simple. Real gases, not so much.
Right.
Okay. So after that, the discussion turns to heat capacities of an ideal gas.
I think there are two kinds, one for constant volume and one for constant pressure. Why do we need two different types? Well, the amount of heat you need to raise the temperature of something, it depends on the conditions. So for a gas, if we add heat while keeping the volume constant, that's an isochoric process, all that heat goes into increasing the kinetic energy of the molecules, which increases the internal energy. And that leads to the definition of molar heat capacity at constant volume. It's usually written as CV. It relates how much heat you need to add per mole to change the temperature by a certain amount while keeping the volume constant. But if we add heat while keeping the pressure constant in an isobaric process, the gas expands and does work. So some of that heat goes into increasing internal energy, but some goes into doing the work of expanding. And that leads to the molar heat capacity at constant pressure. CP figure 19.18 in the chapter shows these two situations side by side.
So CV is like the pure measure of how much heat it takes to raise the temperature. And C accounts for the fact that some energy might be used for work if the gas is allowed to expand.
Exactly, and there's a very handy relationship between those two heat capacities for an ideal gas. CP equals CV plus R, equation 19.1 CEVA. R is the ideal gas constant. And this difference between CP and CV, it exists because at constant pressure, some of the heat has to go into work. Whereas at constant volume, all the heat goes into raising the internal energy and therefore the temperature. And figure 19.11 illustrates this.
Okay, I'm seeing the connection now. Now, the chapter also mentions this ratio of heat capacity is called gamma, which is just CP divided by CV. What's that all about?
Yeah, gamma is important for understanding adiabatic processes. It's always greater than 1 for gases. And table 19.1 in the chapter has some experimental values for CP and CV for various gases. It's also important to remember that for an ideal gas, no matter what process it goes through, the change in internal energy is always given by NCV delta T, where N is the number of moles.
Got it. So that's a general rule for ideal gases, regardless of the path. Okay, the last part of the chapter gets into adiabatic processes in detail, specifically for ideal gases. We know Q is 0 in these processes. Does that make things easier to calculate? And what new relationships pop up?
Yeah, since there's no heat exchange in an adiabatic process, the first law simplifies to delta U equals negative W. So if the gas expands adiabatically, it does work, and that energy has to come from its internal energy, so its temperature goes down. Conversely, if we compress the gas adiabatically, we're doing work on it, which increases its internal energy and its temperature. You can see this in figure 19.20. And by using the first law, the expression for work, and the ideal gas law, we can derive these relationships that hold specifically for adiabatic processes in ideal gases. One is TV to the power of gamma minus 1 equals constant. Another one is PV to the power of gamma equals constant. These tell us how temperature, volume, and pressure relate to each other during an adiabatic process.
So those equations are kind of like specialized versions of the ideal gas law for when there's no heat exchange.
You could think of it that way, yeah.
And I think the chapter also has equations for the work done during an adiabatic process.
Right, there are a couple of ways to calculate the work. One is W equals NCV times T1 minus T2. That's equation 19.25. And there's another form, W equals 1 over gamma minus 1 times P1V1 minus P2V2, equation 19.26. These equations, they're strictly valid for quasi-static adiabatic processes. That means the process has to happen slowly enough so that the system stays in equilibrium internally, but fast enough that there's not much time for heat to be exchanged with the surroundings. But even for real processes that aren't perfectly quasi-static, these equations often give us pretty good approximations.
And I remember that bio application about exhaling with pursed lips. That was a cool example. It's like a mini adiabatic expansion right there in your mouth.
Yeah, it is, and it explains why that feels cooler. When you exhale quickly like that, it's essentially an adiabatic expansion, and that causes the air's temperature to drop.
So that's why it feels cool.
Interesting.
Now, one last thing, that example about the diesel engine, that really brought all these adiabatic concepts together.
Yeah. Example 19.7. It shows how, in a diesel engine, when the air gets compressed really fast in the cylinder, it's basically an adiabatic process. And that compression causes a huge temperature increase. And it's that high temperature that ignites the fuel when it gets injected. So the example, it uses those adiabatic relationships we just talked about to calculate the final pressure and temperature after compression, and also the work done. And it compares that to what would happen in an isothermal compression. And because the energy goes into increasing the internal energy in the adiabatic case, you end up with much higher final temperature and pressure.
Makes sense. All right, so we covered a lot of ground today. What are the key takeaways from all this?
So the first law of thermodynamics, it's basically energy conservation, but it takes heat into account. Internal energy, U, it's a state function, meaning its change, delta U, only depends on the initial and final states, and it's given by delta U equals Q minus W. Heat, Q, and work, W, they depend on the path taken. We talked about the four main types of thermodynamic processes, and for ideal gases, internal energy only depends on temperature. We also talked about the molar heat capacities, CV and CP, and that important relationship between them. And finally, we went through the specific relationships that apply to adiabatic processes and ideal gases.
It's a lot to absorb, but understanding this stuff, it really changes how you see the world around you. All those everyday things suddenly make so much more sense.
Definitely. And to keep you thinking, here's a question to ponder. We know the first law is about energy conservation, and we know internal energy is a state function. So given those two things, what limits does the first law place on our ability to perfectly convert heat energy into work in a cycle? It's something to think about as we keep exploring thermodynamics.
I love a good challenge. Thanks for the deep dive today.
You bet. Anytime.